Okay, so this is one of the. This would be a lecture that requires a lot of drawing. So I don't want to do a lot of drawing, and we're going to go with 18.8 applications of electrostatics. We're just going to do that. We're going to enjoy this little bit. I don't have to write out so much. So let me get here to where got our stuff here. Okay, so Van de Graaff, this fellow named Van de Graaff, came up with a way of generating high energy particles. So for what is it that we're doing with the Van de Graaff generator? We're trying to take electrons and shoot them, or an ion of some kind, and shoot them so that they go into a collision with particle accelerators. What we try and do is collide the subatomic particles or atomic particles or electrons or whatever, protons. We try and collide those with other particles, and the more energy that they have, the kinetic energy would be the 1/2 kx, 1/2 mv squared. The greater their velocity, the higher the energy, and then we smash them up and we look at the parts. Okay, and that's the whole point. Well, so Lord Kelvin said that this would be a way that we could create, on a conducting surface, we could create a large amount of charge, and Robert Van de Graaff built one. And in 1931, I think it says here. So anyway, we're using smooth and pointed surfaces to generate these large voltages and send these charges out. So here we have, it says it's an ion source, a positive ion source. We've got our conductor that is full of positive charges, or minus a lot of electrons. And if we generate ions at this source and we push them through this hole a little bit there, then there's no E field inside this conducting sphere. So all you have to do is shoot them to a point where they get to the outside of the sphere, and then the electric field takes over, right? And if it's a bunch of positive, if the Q on the conductor is positive, then it's going to want to shoot that poor little ion out really, really fast. And then so see where it says to experimental area? Well, the experimental area would be where we would have other things that these fast, the forces on them are enormous, and it really, really accelerates these little guys up to a certain velocity, and then they smash into something. So how does this Van de Graaff generator work? Okay, so if you notice, we have ground here, and there's this rubber belt that you get a motor or a crank or something that is you want it to be insulated so you don't get charged, you don't get the electric shock yourself. Anyway, the belt turns. You can see which direction the belt turns. So it's clockwise at the bottom, clockwise at the top, and the belt then, and it's a rubber belt. And the rubber belt has, at A and B, has the, what do they call them? Brushes. They're metal brushes. And the metal brushes strip electrons away from the, it strips away from the top B, and it pulls electrons away and sends them all the way back down to A. And then when it gets to A, the electrons go to ground. So all the electrons get stripped from your conductor, which leaves your conductor with a lot of positive charged holes. Everything around it, if you can see the, I don't know what that color is, but there's this insulating, typically glass or they use glass so that you can see on the inside, but it could be anything. It could be rubber. It could be, who knows what. Anyway, there's one at the University of Virginia where I went to school for a little bit, and that one is about 12, maybe 15 feet tall to the top of the conductor, and it has a great big ball on the top, maybe, I don't know, 6 feet in diameter, and it could generate, probably close to, they say here you can get up to 15 million volts. And that's about right. That's about what we were getting. And it was genuinely used to do high energy, well, I shouldn't call it high energy, particle physics experiments. So, okay. So they have this battery down here where the ground is. And that battery is what is supplying or taking the electric charge away from this conductor. Anyway, it's the conductor at the top that really is the it's the focal point of the Van de Graaff generator. Yeah. So here we have xerography. Okay. I don't know what is going on here. Did I lock it up? Okay. So xerography. This is how we make copies of things. So we have this drum, and it actually is coated, and they make it coated so that you could put charges on the drum in certain spots, and so like here they have a 3, and the 3 gets lensed onto the drum, and a positive image is made on the drum. So the drum is positively charged. They take negatively charged toner, and they roll the drum through the toner, and then the 3 that has been negatively charged imprint absorbs, or all the negative toner attaches to that 3, and then you run it over a piece of paper, and as you're running it over the paper, you hold on to the paper and make the paper positively charged. So that sucks the negatively charged toner onto your paper, and then the last thing they do is they heat it up to a point where the toner solidifies with the piece of paper. It gets hot enough so that it kind of melts in. And anyway, that's how we use charges to make prints or print out our papers. And then there's laser printers. Okay, so a laser printer does the same thing, only on the drum, the laser shoots at the drum, and that laser, once it hits in certain areas, it charges up pieces of the drum. So here's a number 1, and you can make that number 1 positive. And the same thing happens. You roll that same piece of paper, you roll it through toner, it picks up the toner, then you roll the paper on it, and then the toner goes to the paper, then you heat up the paper, and it firms up your toner on your print on your piece of paper. So an inkjet printer, look at this. Look how this works. An inkjet printer works exactly the same way as the electrons in a CRT, where we have, instead of electrons, we're shooting ink, and the ink gets charged up. So there's an ink reservoir. The ink reservoir sends to the ink nozzle. The ink nozzle sprays some, gives the droplets of ink. It gives them some initial velocity, so they'll go through the charging electrode. The ink then gets charged up and run through deflection plates, which will either be positive or negative depending on which way you want to aim it. There's 2 sets of deflection plates. There's the up-down set and the side-to-side set. We're just showing you the up-down set, but you can rasterize. If you have both sets, you can go up, down, and side-to-side, and that direction shoots your aims where that droplet needs to go next. So they call it an inkjet printer because you're shooting it out in a jet. It gets charged as it goes through the deflection plates and then hits your paper. And once it hits the paper, it just kind of sticks there. You have to let it dry. I don't know if they heat that one up. So that's an inkjet printer, and that's how that works. Electrostatic painting, you can do the same thing. Okay, so smoke precipitators and electrostatic air cleaning. All right, so here we have some plant. Maybe it's a coal plant or a natural gas plant. You can tell natural gas plants from coal plants. See the conveyor belt in the middle there that lifts up? It looks like it's taking something up on a conveyor belt. That's coal. However, a lot of coal plants have been upgraded to natural gas, and the conveyor belts that go up these into the actual furnaces, those conveyor belts don't always get taken down or removed. So a lot of plants are now CO2 plants. Natural gas plants versus coal, which is good. It's not great, but slightly better. Okay, so here's one of the ways that they take the exhaust, instead of spitting it out into the atmosphere, all of the particulates and other assorted things from a coal plant. So let's say it is coal. You get a lot of stuff other than clean gases. And by clean, I mean clear. So a clear gas will come out. It might be still a greenhouse gas that comes out, but it's not a gas that is necessarily one that causes smog or haze or any of that stuff. So they want to scrub the coal, the byproducts of the coal. So incoming, you can see on the left, here's A. At the very bottom, we have this incoming exhaust from our fire, smoke. That incoming smoke has a bunch of junk in it. And so then it goes into a filter, just a regular old filter. A lot of the times they use water for that first filter. And the water, the particles, sometimes they interact with the water and they get absorbed into the water, but a lot of the neutral particles will come through and, or they come through as a neutral particle, and then they get charged. So they go through this next screen, which is not a filter, it's just a positive charged screen. Actually, it's a negative charge screen that strips electrons away from the particles. And then those things end up going to this negative screen. And they get, because they've had their electrons stripped, they want to attach to that other screen. And the screens actually are just like the conveyor belt in the Van de Graaff machine. They're conveyor belts as well, and they get cleaned up. So they rotate and get cleaned up as these things go through them. They get brushed off at any rate, and that material gets collected and piled up as dirt or gross, whatever. It's gross. But anyway, so what you get after that is not a lot of the particulates going through the air anymore. And so then your final filter, which is very similar to your initial filter, it can even be a finer filter than the initial filter. But that final filter will take any of the rest of the particulates, it will take them, collect them, and you can move on. I have no idea why we're talking about problem-solving strategies for electrostatics at this point. I don't know. Read that if you want to. These are the same strategies that I tell you when we're solving problems, and I'll go into those, what you need to know when we do our review for the second test. So let's talk a little bit about acceleration of a charged drop of gasoline. So the reason why they're doing this is because let's say you're at a gas pump and there's static electricity around. Who knows, maybe your car is positively charged and a little bit of the gas comes out negatively charged. Then the negatively charged gas will get attracted to your positively charged car. But if it's positively charged gas, it'll get shot away from your positively charged car, and then it goes out into the atmosphere, and you could be blowing fumes out from your car. And if you were to light a match or have a discharge of a spark or something, then the next thing you know, you've got a whole bunch of tiny droplets in the air of gas and a lot of oxygen around, and it just blows up on you. So that's the whole point of this this thing. anyway, I was going to talk about, just now it started making me think about fuel injectors, but it's a similar thing. Okay, so you have a fuel injector, it sprays the gasoline in a fine mist into the engine, the cylinder, the empty cylinder on an engine, and then the piston comes up, compresses it, ignites it, and you have an explosion. So same thing. So here we go. We've got a tiny drop of gas that has this really tiny amount of mass, and it has a positive charge, 3.2 times 10 to the minus 19 coulombs. We want to find the weight of the drop. Okay. So the weight of the drop, we just take that mass and what? Multiply it by G, right? Okay, so that's easy. We're going to calculate the electric force on the drop if there is an upward electric field strength of 3.0 times 10 to the 5th nanos per coulomb. And maybe due to some electrostatic forces in the vicinity. And then we're going to calculate the drop's acceleration. So first thing, here we go. The weight is equal to mg, and that's a no-brainer right there. Hopefully you guys can easily do that. Second, the force on the electric field comes from F equals Q times E, and they gave us the magnetic field strength, electromagnetic field or electrostatic field. That is 3.0 times 10 to the 5th nanos per coulomb. So we've got that, and so we know what E is, and we know that the positive charge of the little droplet is 3.2 times 10 to the minus 19 coulombs. So there's our Q. So all we have to do is multiply those two things together. They're an 18.23, and you'll see that we get 9.6 times 10 to the minus 14 newtons. Okay, and if they're both positively charged, which it looks like they are, then that force is going to send the positive charge away from wherever the electric field is, pointing away from the positive charge. So it might be your car or whatever. It's going to throw it away from the car. So it's a small force, but it's much greater, right, than the drop weight. So it'll still shoot it up into the air because it's 9.6 compared to 4 and more than double. So it will definitely shoot that thing up into the air, and then we can figure out what the acceleration is by taking that net force and dividing it by m. So our net force in this case, this is unlike problem 11 of this week's homework, because in the y direction we have the downward force of the weight, and we have the upward force of the electromagnetic force. And you can see that here we've got 18.24, A equals F net over M. But the next sentence where F net equals our electromagnetic force minus our mg, okay? So our weight is not insignificant in this case. However, in problem number 11 this week, it is insignificant. So you have to look at the size of the forces involved. So 18.21 we've got times 10 to the minus 14 newtons, and 18.23 we also have 10 to the minus 14 newtons. So the orders of magnitude are definitely the same. So since F net is F minus W, we divide that by the mass, and we end up with 14.2 meters per second squared, which is, 1.5 Gs. So it's going up at 1.5 Gs. And that seems about right. I'm reading this unreasonable results thing here. I didn't read this before. Doesn't look like it's unreasonable. So I think that's just applying to the whole chapter. There could be some things that seem unreasonable in this chapter, I suppose. And then here's some more problem-solving strategies, which I will talk about. So that's it for this this last bit of chapter 18, and I'm going to record another one on chapter 14. So